Hi, I'm Manfred. As Kim said, I'm a PhD student at the University of Idaho, originally from all over the US. But today I'm going to be presenting on soil carbon dynamics in manure-amended systems. Now, we are pretty early into this research, so I'm going to go through a little bit of background and then our research questions and where we are at in the research itself. So this is Bill Dairy, and the intersection of soil science and dairy happens to generally be at the manure side of dairy. Waste management is a huge part of dairy production, and in Idaho alone, there's about 700,000 dairy cows. On a daily basis, that's about 40,000 tons of manure. Now, I personally can't think of how much manure that is. So, putting that into an equivalent volume, that's about 280 coal cars worth of manure produced every single day. So, they have to do something with that waste. And that generally ends up as application to soils. And that is because there's a variety of benefits associated with applying that manure to soils. The biggest one is a nutrient benefit. So, there's nitrogen, phosphorus, potassium, as well as a bunch of micronutrients in that manure, and so it is applied to soil to offset fertilizer costs. In addition, manure has a lot of organic carbon in it. And when organic carbon is in soil, there's a lot of other benefits associated with it. They're both physical, chemical, and biological. With physical benefits such as aggregation, this makes the soil less likely to erode, and it makes these little cohesive aggregates that form structure for water to go through. It reduces bulk density, so it's easier for roots to actually grow into the soil, and so plants have an easier time growing. And both of those combined increase the amount of water that goes, or the speed at which water will enter the soil. In addition, it increases the amount of water that soil can retain. Chemically, organic carbon has what is referred to as cation exchange capacity. So some nutrients are cations in nature, and so this organic carbon allows the soil to hold more of those cationic nutrients. And in acidic systems, there's also a benefit by increasing pH, which makes a more beneficial environment for the crop to grow in. On a biological side, organic carbon stimulates microbial activity. Microbial activity is one of the foundational aspects of soil health, so increasing organic carbon is typically associated with increasing soil health. In addition, that microbial activity leads to the cycling of nutrients from organic forms that are not plant available to inorganic forms that a plant can use, so it is increasing the amount of available nutrients in the soil. And finally, carbon sequestration is a big part of understanding soil carbon and a reason to apply carbon products such as manure to the soil. As noted, there is a lot of benefits by increasing organic carbon. And in the case of mitigating climate change, soils are seen as this really good potential source of increasing the amount of carbon stored as opposed to released. This kind of brings us to the discussion of the carbon cycle. These are values for a global carbon cycle. Everywhere there's an arrow means it's a movement between a pool, so like the atmosphere to the ocean or to land. And all of these numbers are in petagrams of carbon. Petagram is, I do not remember how many zeros there are, but it is a lot of zeros. In the context of climate change, all of it is really attributable to this plus 5 petagrams of carbon per year entering the atmosphere. In contrast, soils are actually the largest pool of carbon in a terrestrial system. If we could increase soil organic carbon by just 1% of that value, that would more than offset all of those anthropogenic CO2 emissions that is associated with climate change. So a large part of understanding carbon cycling is understanding it in this global context of climate change and the carbon cycle. However, that's really not the full picture of carbon in soils. In fact, that 1,500 petagrams of carbon number is really just the top 1 meter of organic carbon that's in the soil. If you go deeper, there's quite a bit more carbon stored in the soil. And then there's this whole other value, soil inorganic carbon. Soil inorganic carbon is really not looked at in the context of the carbon cycle, uh, partially because it's assumed to not be interacting with it. Inorganic carbon in soils are typically carbonate minerals. As we get into arid and semi-arid environments, up to 90% of the carbon in soils might actually be inorganic. In the context of southern Idaho, where a lot of my research is taking place, 65% of the soils in the Magic Valley, where the main dairy producing region of Idaho, contain inorganic carbon in the form of carbonates. They're entering the system through hard irrigation water. They might naturally be naturally occurring as like limestone bedrock that's underneath the soil, or anytime you apply agricultural lime, you're applying inorganic carbon to the soil. But this is thought to have a really slow turnover. So inorganic carbon is thought, or carbonates are thought to stay in the soil for about 80,000 years, which is a lot different than the 50 years or 100 years, even 500 years that we discuss for organic carbon and its residence time in soil. We do see it appear a little bit through the export from terrestrial landscapes to the ocean in this like zero point 0.4 number, but that's really not the full picture. Again, in soils, the amount of inorganic carbon is almost equivalent to the amount of organic carbon. The other part of carbon dynamics we're going to be focusing on this research is dissolved organic carbon. This is a small portion of total soil organic carbon, probably about 5%, but is very sensitive to management practices. On the left of this image, this is a soil water extract. So we just shook the soil with water and to see what would come out of it, in this case, looking for dissolved organic carbon. And we did the same with manure. It's really hard to tell in this version of the picture, but that is actually all liquid on the top of that manure test tube. And all of that dark brown liquid is the dissolved organic carbon. So in the case of manure, we're directly adding dissolved organic carbon. And there's a lot of implications around the downward transport of organic carbon in these systems and how carbon might be migrating to deeper depths. Uh, Dissolved organic carbon can also make metals more mobile, as well as has interactions with other contaminants as it is reactive. And then because of that reactivity, it does interact with soil minerals. And the ones of interest for our research are going to be carbonate minerals. And that kind of brings me to our research questions. The first one is, do manure and manure-derived amendments impact soil inorganic carbon content? Again, because it interacts so slowly in the carbon cycle, it is a really overlooked part of understanding how soil carbon moves. Then, does dissolved organic carbon content and composition vary with the depth? And then finally, can we identify the manure-derived carbon apart from other types of soil organic carbon that might be present, especially that native soil organic matter? To answer these questions, we're looking at three different projects that are all long-term studies at the ARS facility in Kimberly, Idaho. These are the long-term manure project, which received different applications of manure at varying rates for about 8 years until the high rate got to have an excessive amount of phosphorus, and so they stopped applying manure. And it has been in drawdown, so no new applications for about 6 years. We're also looking at the GraceNet project, which has received dairy manure compost for 2 out of every 5 years during its crop rotation with 6 applications total, and that project is going on its 14th year. And then the FFAR project, which has manure products, byproducts really. So these are the byproducts of industrial like dewatering processes of manure applied 2 out of every 5 years. And that project was initiated in 2020. And we went and sampled these soils back in August of last year. And we took our samples at 0 to 15 centimeters, which is about 0 to 6 inches, 15 to 30 centimeters, 30 to 60, and 60 to 90. So we essentially sampled all the way down to 3 feet. In order to investigate the inorganic carbon content and whether or not we can distinguish that manure-derived carbon, we've got a couple different approaches. The first is using an elemental analyzer with an isotope ratio mass spec. This is essentially going to combust our soil sample at very high temperatures and will measure the amount of CO2 that it comes off of those samples, as well as using some different processing methods to get the particular of organic carbon or inorganic carbon. This is essentially going to just tell us changes in carbon content. And then the mass ratio part will actually tell us something about where this carbon originates from. Isotopes are just different numbers of neutrons on the same atom or same type of it or same element. And variations in the isotope ratio are actually indicative of different formation processes for all of these different carbon compounds. So seeing different ratios will imply different sources of carbon in these soils. We're also going to be using thermogravimetric analysis, which is slow heating of a sample and measuring the mass loss at every temperature increment that we are able to. And this essentially gives us a thermal stability curve, and thermal stability is highly related to biological stability as well as chemical stability. So if we see shifts, especially shifts downwards from the application of manure in the thermal stability of the organic carbon, it would be implying that that manure might not be as stable as naturally occurring soil organic matter. Similarly, if we see shifts in the downwards in the thermal profile of inorganic carbon, it would be implying that there's a lot of processes around precipitation or dissolution and reprecipitation of those carbonate minerals, which will tell us that there's more and more interactions going on between that manure product and the inorganic carbon in the soil. For dissolved organic carbon, we're going to be looking at water extractions. There are other ways to get at dissolved organic carbon, but this felt most relevant to the system, as we're focused on carbon that might be transported from things like irrigation water or precipitation. In order to get our dissolved organic carbon content, we're going to throw them on a combustion analyzer that's going to heat up our sample and again measure that evolved CO2. And then we're to get at the quality of that carbon, so what that dissolved organic carbon might be look like from at a molecular level. We are using absorbance and emission fluorescence spectroscopy, which is an instrument called an aqualog for us. And that is going to essentially measure the adsorption of light at every discrete wavelength, as well as light that might be re-emitted from that sample at every wavelength. And based on those patterns, there are characteristics specific to different types of compounds that will allow us to identify what kind of dissolved organic carbon compounds we have in the in those samples. So far, we have sent out some samples for commercial analysis immediately after, so we could get a whole suite of values done quickly. On the left graph here is organic matter on the x-axis and depth on the y-axis. And so this is going to be from the long-term manure study, with green being the high manure rate with 52 megagrams per hectare, blue being the low manure rate of 18 megagrams per hectare, and that red line being the control. The graph on the right is that same depth on the y-axis with calcium carbonate equivalents, which is a stand-in for inorganic carbon content on the x-axis. As it turns out, when you apply a lot of manure, you do in fact increase soil organic matter. That was not terribly surprising, but we only saw changes down to about 30 centimeters. So that top 1 foot of soil increased in organic matter content, despite having 52 megagrams per hectare applied every year for 8 years. Oddly enough, or I guess unexpectedly, we saw calcium carbonate equivalents decrease in the high manure samples and maybe the low manure rate. And these are happening at the lower depths. So this is really probably going to be important with the interaction of dissolved organic carbon content, and organic carbon and inorganic carbon, as there has to be something mobile to cause that dissolution. Currently, we are working on evaluating that dissolved organic carbon content. This was done about like a week ago, and it is following broadly that same trend of higher dissolved organic carbon in the high manure rate samples, but it appears that that elevated dissolved organic carbon is continuing into those deeper depths. Our next step is actually to take all of these samples and start understanding how to do the molecular characterization process. And it is taking this graph here on the left, which is a raw, unprocessed excitation and emission spectra, also called an EAMS, and turning it into this graph in the middle, because that graph on the left has nothing of interest there. It just looks like a blue background. As we go through the data processing and signal optimization, we end up with this graph there in the middle that is essentially giving a fingerprint of some sort of compound that is occurring in our samples. And based on other literature, there is very discrete classes of compounds that are producing that type of adsorbance and emission spectra. And we'll be working on correlating the types of compounds we are observing with what class of compound or what region that data is occurring in. In summary, this is research really investigating the dynamics of inorganic soil carbon in manure-amended systems, as it's really understudied and might represent an important change in the system. We're also understanding dissolved organic carbon and mineral interactions to further predict those soil carbon dynamics, as this organic carbon is moving downwards, and it would be good to know if it is going to have meaningful changes in depth. And ultimately, we do want to leverage this research to understand and improve the sustainability of manure applications, as understanding where the carbon is going and how long it is staying there is a really important part of the long-term sustainability of manure applications. Just some quick acknowledgements. Thanks to my collaborators and Bill Dairy funding this, as well as the USDA Idaho Sustainable Agricultural Initiative for Dairy, and of course the rest of my lab. And here are some random highlight photos from some of the work I've done. Oh, questions? Just gonna scroll all the way through there. There we go.
Okay, while we're waiting, I have a question. What, throughout your research, what challenges did you face and how did you overcome them? Or one challenge, whatever.
Right now, I'd say we're currently in the challenge phase of my research. So we are dealing with, right now, the hardest part is figuring out what filters we can use that allows us to get enough volume through without putting a contamination signal on our samples that isn't crazy expensive, and is doesn't require washing every like 10 samples. So right now we're really like deep issue phase. And
Okay.
it's all logistics and methods.
All right. Can you see the chat?
Yes, I can. Carbonate is not in, oh, so the question is, why is carbonate in the soil bad? Carbonate in the soil is not per se. It is generally naturally occurring, and so it is more like a condition that exists. The reason we're looking at it is we do not is that we actually like it to stay, because it is a potential source of carbon that is overlooked in understanding the carbon cycle. In some cases, it does mean you have like an high pH in the soil, but again, that's a condition that exists, and you kind of adapt to it rather than having it be like a bad thing.